Buenas tardes, bienvenidos al ciclo de seminarios del Departamento de Química, trimestre 24I. El día de hoy tenemos a un ponente especial invitado y bueno, agradecemos como siempre la presencia de los que nos acompañan en el Salón de Seminarios R206 y de manera virtual en el enlace de YouTube. Antes de comenzar con la presentación del ponente, vamos con los anuncios que tenemos para ustedes. Bueno, los seguimos invitando a que nos escriban al correo de seminarios, el cual aparece en pantalla. Los responsables somos servidor doctor Edgar Carrera Crespo y doctor Víctor Manuel Trejos Montoya. También los invitamos a que escriban al podcast, quieran participar o sus comentarios. El correo aparece en pantalla. Los responsables son el doctor Ricardo Peralta Ávila y la doctora Lucero González Sebastián. También los invitamos a que participen y escriban a la Gaceta Tlecachil. El correo aparece en pantalla y los responsables son el doctor José Luis Córdoba Flums y el doctor Humberto Laguna Galindo. Y asimismo los seguimos invitando a que visiten nuestros sitios en internet, la página de YouTube, Facebook, Twitter y la página web del Departamento de Química. Y bueno, para la presentación del invitado del día de hoy, le cedo el micrófono a la doctora Ania Galeano. Adelante, doctora.
Good afternoon. Thank you all for being here. It's my pleasure to introduce Professor DiLabio. He's a field professor in the Department of Chemistry at the University of British Columbia of Canada campus, which he joined in 2014. In addition to methods development, his research interests include know-how, behavior of radical enzymes, radical chemistry in general, and electric field catalysis at water interfaces. Prior to joining UBC, he was a senior staff scientist at Canada's National Institute for Nanotechnology, now the Nanotechnology Research Center, where he worked on the development of novel quantum cellular automata and hybrid organic silicon systems. He has published more than 150 papers, patents, and chapters. Welcome. Thank you.
Thank you, everyone, for attending my talk today. I really appreciate your participation, and I think we can have a discussion about the material that I present today. So the title of my talk is here. I won't repeat it. Perhaps we can go to the next slide. This is an outline for today's talk. I'm going to share with you a little bit about some of the other things that we do, and then I will talk about our approach to improving quantum mechanical calculations, that is, their speed and accuracy. And I'll talk a little bit about the development without going into too much of the computational or programming mess that accompanies it. I'll focus most of my time today on the applications and some of the next steps. We, as Anya said, we do a lot of work in physical organic chemistry. It's something we've been doing for about 20 years in my group, and one of those things that's kind of trying to shake once you start doing it. And here's an example of a recent work with my colleague, good colleague and friend, Massimo Pinetti at the University of Rome, on exploring the Allen-Talani principle. So Massimo's group is known for doing very accurate time-resolved laser flash photolysis kinetics on hydrogen atom transfer reactions, and we performed accompanying computational work, and we were able to interrogate the 100-year-old Allen-Talani principle and show that in fact this is at least a fine model that we need to do, contrary to Allen-Talani principles in the literature. Next slide, please. We also do a lot of work with polymer chemistry. We do classical molecular dynamics simulations to explore how changes in atomic structure of polymers can lead to improved properties in a particular direction. For example, or changes to glass transition temperature or Young's modulus and so on. But what we're really interested in is developing new molecular species that can serve as polymer cross-linkers. And we've used these cross-linkers to improve the strength of materials that could be used for ballistic protections, or for vests, for soldiers. Lots of fun, and students, I think, also have a lot of fun with this. On our campus, we have a ballistic, experimental ballistic range. So we can take these materials, treat them with polymer cross-linkers, and then directly test the improvements in the strength of these materials by shooting bullets at them. So it's a lot of fun. And then, I'll tell you a little bit about this non-alpha behavior, and I'm happy to have discussions after the presentation about this. This is the work of my PhD student, Hossein Khalidian. He's been studying radical enzymes. When I first came to this area of biochemistry, I learned that there are 700,000 radical enzymes that are critical for life of different kinds. This is glutamate mutase enzyme that Hossein studied as part of his master's degree. He looks much older than this now, gray hairs and so on. And so in glutamate mutase, this adenosine fragment, which you see on the left part of the screen, dissociates from cobalt Baldwin adenosine fragment that's in the active site protein. And then that radical migrates through the active site and abstracts a hydrogen atom, and just one hydrogen atom from a substrate. So along the way, there are many hydrogen atoms that it can choose to extract, but it only extracts that one. So the question that we ask ourselves is, what kind of a mechanism is the enzyme using to control the behavior of this highly reactive radical species? And this is a primary carbon-centered radical built from years of experimental work, and that's highly reactive. It should grab any hydrogen that it wants, but it doesn't. And it turns out that this adenosine radical displays a very unusual behavior. Next slide, please. So that's it. Migrating. Sort of, slide after that. Next one. Thank you. It displays this very unusual behavior. We learned in first year chemistry or high school chemistry that when we write down the molecular or atomic orbitals for a system, we start at the lowest energy and work our way up, and we put the electrons in those orbitals starting from the lowest, and we finish when we run out of electrons. In the case of a radical species, we normally expect the unpaired electron to live in the highest energy orbital. So singly occupied orbital is usually the highest energy orbital. These adenosine radicals, though, display something very unusual and very hard to understand. That is an electronic structure where the unpaired electron resides in an orbital that's much lower energy. This is termed SOMO homoinversion, or SHI. And when we first discovered this, we thought we made a mistake, and then we thought maybe we were crazy. Then we tried to write a paper, and the reviewer said you're crazy. And that was in around 2020. And when we, as we continue to work through this to figure out better ways to convince the reviewers, other works have come forward to indicate that SHI is not as esoteric as it is in these enzyme systems. So Jean-Luc Verdun, for example, has developed a whole series of photoluminescent radical molecules that are highly stable radicals, and they all display some homoinversion. And so we think that the findings of Verdun relates to how the singly occupied orbital is very low in energy, and that is what helps to confer stability on this photoactive materials. So if I'm crazy, then Jean-Luc Verdun is crazy as well. So good company. Next. So in the case of the adenosine radical, if this SOMO homoinversion confers stability on the radical, that might explain the mechanism by which these enzymes are controlling these highly reactive radical species. And so in that transition of the adenosine from just dissociating from cobalamin to migration over to the substrate is, we notice that there's a significant change in the hydrogen bonding character associated with the adenosine. So before migration, there isn't really a hydrogen bond between this glutamate, and then when the adenosine makes it over to the substrate, there's a very strong hydrogen bond between the glutamate and the adenosine. And next slide, please. And it turns out that before it gets to the substrate, there's a high degree of somal inversion, which tells us that maybe that radical is much more stable than it would be otherwise. And then when it gets to the substrate, there is a much smaller somal inversion, which indicates to us that perhaps this is more reactive. And in fact, when we calculate the barrier heights associated with these reactions, we see that this is in fact the case. So this is a very compelling, kind of cool, weird finding that we have here. Maybe these radical enzymes are using somal inversion and changes in non-covalent interactions to control the reactivity of atoms. There are 700,000 of these radicals, radical enzymes, as I mentioned. So this can be offering some new insight into how they work. Next slide, please. This is the last bit of introduction to our group's work, and I wanted to share this specifically because this is the work of recently graduated PhD student in my group, Eduardo Romero, who came here from UNAM, came to my group from UNAM. And he was particularly interested in these reactions that occur at water-oil interfaces for water-air interfaces. This is water-oil, and this is work done by Sharpless in 2005. And he showed that if you just take these two reactants, meet, that the reaction time to completion is about 2 days. But if you add some water, and water is immiscible in this system, so you're creating an interface, the reaction time drops substantially. So clearly, the water-oil interface is doing something to accelerate this reaction. So Eduardo explored this in his, there's the picture of Eduardo, which should have been on the previous slide. He explored this in a number of reactions. I'm showing here a simple Claisen rearrangement where X is oxygen or nitrogen group. And he showed that that with fairly small applied fields, so electric field associated with hexane or water at an water at an interface, we can significantly reduce the reaction barriers associated with this particular reaction, but the other ones that studied as well. And Eduardo also did some molecular dynamic simulations and probed the interfacial electric field here and showed that, in fact, at the interface, we see electric fields that are large enough to significantly catalyze reactions that we studied. So nice work by Eduardo. He's now moved on to a postdoctoral position at the University of Alberta. And our next steps in terms of these studies will be related to exploring how air-water interfaces can lead to the creation of molecules for life from methane. So that'll be neat. Slide, please. Oh, there's this model. So I won't spend too much time on that, but we can talk about it later. Okay, so here's the main presentation, and I'd like to acknowledge the folks who've done a lot of hard work on this project. Primarily, Alberto Otero de la Rosa, who is a research assistant with me at the University of British Columbia. He's now at the University of Seattle in this independent position. We're still working quite closely together on this. I think he likes it more than I do. And Vicky Kumar Prasad, who's also a recent PhD student who did a lot of, in fact, the entirety of his thesis was focused in this area. And he's now got a faculty position at the University of Calgary. And two current current students, Mas is a PhD student and Amit is a MSc student at this. Next slide, please. Okay. So here's the motivation for why we're doing this. I think anyone who's tried to run a Gaussian calculation or anything else knows this problem, cost accuracy problem. And the kind of black arts part of computational chemistry is deciding how quickly can I do a calculation and get a result that I can rely on, that I can use. And so this plot here sort of illustrates all of that. On the blue line that you see here is the error that you get in the binding energy for this thymine, adenine thymine dimer. And this error in energy is really just relative to the quadruple zeta basis set that I'm showing here. For all intents and purposes with DFT, that's the complete basis set. And the corresponding, the black line corresponds to the calculation, relative calculation time associated. So if you want to get down to complete basis set sort of results using density functional theory, relative to just a minimal basis set or a single zeta basis set, you have to pay 4 orders of magnitude of calculation time. So this is the balance that we have to try to achieve. And so, and this is what was happening to this project. We started this with some general hypotheses. We hypothesized that in the wave function or density that we calculate at a particular level of theory, that the errors associated with that approximate wave function are somehow contained within that function. In other words, we know when we're getting bad results, and we have some idea of what's deficient about the wave functions that we calculate. We also hypothesize that it's possible for us to construct an operator that we can include with the Hamiltonian associated with our calculation in such a way so that we can extract an energy from that deficient wave function so that it corrects the approximate energy that we get from that wave function to give us a better energy. And since in computational chemistry, almost everything we do is related to the energy that we're calculating, this seems to be a valuable thing to try. And so this isn't really a hypothesis, it's a fact that the potential, this potential that we construct, in principle can take on any form, provided that it doesn't violate the principles of quantum mechanics. So we know how to do that. We know quantum mechanics. We know how to construct appropriate operators. So the big question was, do we have a technology that we can utilize to implement something like this? And it turns out that we do. The work that we're doing relates to atom-centered potentials, and codes like Gaussian have input to allow us to use effective Bohr potentials, which are atom-centered potentials. For those of you who aren't familiar with effective Bohr potentials, they're used in molecular calculations, typically when you have transition metals or heavy elements. And they're used in the past because, well, computers in the past were terrible, and if you can get rid of some electrons, you can speed up your calculation. So if you wanted to do a calculation in 1970 on lead chloride, you would probably use an effective Bohr potential to replace a lot of the core electrons in lead just with a simple potential that has this Bohr. And that would speed up your calculations. The other advantage to using these effective Bohr potentials is that you can introduce scalar relativistic effects into your calculation as well. So that's kind of cool. But this technology is built into most computational chemistry programs out there, and it's been in there for decades. So nice approach for us to use. This is an operator that gets added into the Schrödinger equation. It gets added to the Hamiltonian, and it spits out an energy for us that maybe if we can co-opt this approach, we can use it for our hypothetical atom-centered potentials. Long story short, we've done all of that. So I'll show you firstly how these effective potentials are used in a Gaussian kind of input. I think that's on the next slide. And here we are. So in this top portion here, there's lead PBH4. And this input file, actually, can you flip back one slide, please? One half slide, yes. Yes, straight. There you go, there. So this is a standard Gaussian input file. If you wanted to use effective core potentials for lead for pH4, this is how you would build the input file. Probably looks familiar to most of you, except for the zoom bar at the top. But you would use your favorite functional, and you would call the effective core potentials using the Q something. Another way you can do this is to read that effective core potential and the basis set by appending the input, and that's the next half of the slide. There you go. So this is exactly the same input, except I changed the basis set to its gen P keyword, which says read the basis set and the effective core potential from the input file. And this is what it looks like. These are just terms in a very simple Gaussian expression, where the red numbers are the powers of R in the expression in the red box. The blue are the exponents, and the green are the coefficients. So in doing this, I can throw away the most of the core electrons in lead, and I can speed up my calculation. Next slide, please. Okay, so these effective core potential things that we already have built into programs like Gaussian and Orca and so on, are our solution to the cost accuracy problem. Since this potential that we're constructing can take on any form, provided it doesn't violate quantum mechanics, and since effective core potentials already been used for decades in this area, this is an ideal solution. And it's already built into the technology, so we don't have to worry about recoding or rebuilding other people's codes. We can design these potentials and then use them as input in our simulations. Okay, the primary difference here is that while effective core potentials are designed in such a way so you don't have to include the core electrons in something like lead. In our case, we're not replacing any electrons at all, but we are applying the potential to all of the electrons that are in the system. And that's where we're getting our energy corrections from. Okay, so here's a very, very simple example. In the early days of this ACP work, we didn't have dispersion built into density functional theory. In fact, it's mostly still not. And nowadays, dispersion is incorporated into density functional theory calculations using empirical corrections. But here's how we can do it with our ACP terms. So here I have the methane dimer system. If I try to calculate the binding energy using B3LYP or most other density functionals, it's completely repulsive. That's because density functional theory doesn't have dispersion physics built into it. What this potential energy curve should look like is the black curve here. This is a complete basis set coupled cluster, and so on. Okay, well, can I fix the B3 lit curve using one of these potentials? Yes, I can. The next click will show us that with a potential with this exponent and this small coefficient, I can introduce attractive behavior potential energy curve. And I can do it again, get closer to the expected curve. And I can continue this process and develop a full set of these Gaussian type functions to perfectly reproduce this curve. Now, that's great for this one curve, but can we do it for a whole bunch of things? And yes, we can. So just before moving on, can't quite see it. Next slide, please. This is just how we would use the ACPs, exactly the same way we use the ECPs, and it's just appending the input file with, we can't see it here on the screen, unfortunately, in the room, but it's using the gen ECP keyword in Gaussian and other programs. So okay, next slide, please. All right, so we think ACPs can mitigate all sorts of errors, not just dispersion, and who cares, because there are dispersion techniques available in LDMT that work very well. We've already done that anyway, and nobody uses it, so it doesn't really matter. But beyond just correcting for the absence of dispersion in Hartree-Fock and density functional theory, we think that we can correct for many, if not all, of the underlying deficiencies in any theoretical methodology, whether it's density functional, generalized gradient approximation, or a double hybrid. We think we can use it. And that includes delocalization error, the structure of the exchange of correlation functional, self-interaction error, and so on. And we think we can also do it with wave function theory applications. So if we take archery clock, we have zero correlation in the archery clock method. So we think we can use ACPs to predict fairly well what that correlation energy should look like on the basis of the archery clock function. And we know we can correct for basis setting complete. So I'll show you for the bits in green, I'll show you some results today. And then I'll finish up with where we're going related to fixing wave function theory methods. All right, so why should these ACPs work? Well, here's a density difference plot. This plot here is showing for the water dimer in hydrogen bonded arrangement what the density difference looks like between complete basis set archery clock and minimal basis set archery clock. If we think about how this density difference works and relate back to the effective pore potential or ACP equations that we're using, we see that this error in density as we move away from the nuclei, that decays exponentially. So we have this exponential form in Gaussian functions. And around the nuclei, of course, we have anisotropic behavior, and we can introduce that anisotropic behavior through the spherical harmonic terms in ACP in these ECP, ACP equations. If I showed you here a plot, it's probably the next click. Yeah. So if I showed you here a plot of the density difference in highly correlated wave function complete basis set versus archery clock with complete basis set, the plot would look very much the same. I'll be honest, this isn't the same plot, but if I put the plot associated with this on the screen, we would almost any solution. So again, to fix these problems, it seems that this mathematical approach is a good solution. All right, so I'll walk us through the development workflow for these ACPs that I'll show you around. We start with parameter selection. So because these are atom-centered, we need to identify which atoms we're going to develop them for. And the work that we've been doing most recently has been focused in the area of organic chemistry, biochemistry. So we stuck to those 10 atoms. We choose the terms associated with our ACP. And we do this really just for efficiency reasons. We don't optimize the exponent associated with the terms. We only optimize the coefficients. What we do is we select a range of these exponent terms, and then we select out which ones do the best job at solving the problem. Then we choose a method in the basis set. So it can be anything, minimal basis set, archery clock. It could be a double hybrid density functional theory, any size basis set. Whatever errors are associated with those computational methodologies, the ACPs will be designed to fix or mitigate. The next stage is to assemble a data set of accurate chemical data. Previous work has focused on chemical properties, so we would go out and collect a bunch of chemical properties, and if they're not available in the literature, we would calculate them themselves using the wave function theory. Bond energies, barrier heights, reaction energies, and so on. And then we would subject our ACP terms to optimization through a method that's referred to as lasso. This is a optimization method that's used in the machine learning community. And what lasso does is not only does it optimize, it's not showing up. There it is. Not only does it optimize the coefficients associated with our ACPs, but it also throws away Gaussian functions that don't contribute to the improvement of the functions itself. So we start off with a large list of Gaussian functions in our ACP lasso process optimizes the coefficients associated with those and eliminates functions that are not helpful. So in the end, we have a fairly small, compact, effective potential that can be used to directly be calculations. Right, so let me tell you about ACPs for basis set incompleteness. This is a big problem. Many of you worked on this with respect to counterpose correction and so on. This has been, this really relates to that very first plot that I showed you, the cost accuracy problem. We had very large basis set, low error, small basis set, gigantic error. Can we go somewhere in between and make up somehow? So we focused on the development of ACPs for basis setting completeness to tackle that problem. And to do this, we chose a single functional B3 lib. We pulled together a bunch of reference data, properties that we were interested in, obtained using the complete basis set, and then we looked to correct the basis set incompleteness associated with these small basis sets. This is NES basis set. If you're not familiar with it, is a single thing basis set. These are common double-state basis sets. So what did the results look like? Well, for our reference set, we had non-covalent interactions and bond dissociation enthalpies and a few other thermochemical properties. And with our minimal basis set, we found that for the non-covalent interactions, we saw a fourfold improvement in the predicted non-covalent energies. We saw a terrible performance with thermochemistry. Not terribly surprising, you cannot do thermochemistry with a minimal basis set. And regardless of how good this ACP process is, the errors are too large to go. So that's fine. Looking at the double zeta basis sets on the next click shows some of the more favorable performance for the non-covalent interactions. Again, we see 4 to 6-fold improvement in the prediction of interaction energies with respect to basis set completeness, and for the thermochemistry, 3 to 4-fold. So pretty good. So what does this mean? Well, it means if you take this double zeta basis set and you calculate thermochemistry, thermochemical properties with it, you'll get to within, on average, within a half a kcal of the thermochemical properties you would get if you used a complete basis set. But you would be spending about 100 times less computational time doing this. So that's pretty positive. So as I said, we can't really do thermochemistry at the minimal basis set level, but we can get reasonably good non-covalent interaction energies. And so that means then that we can use this approach if we want to calculate energies associated with large molecular systems and maybe do optimizations on proteins and so on. And we were playing with some of that earlier. But here's a good example of it. So this is a small protein called crandin. It has 642 atoms in it. And we're looking at the basis set incompleteness error associated with this protein in a folded and unfolded state. So this is just the delta energy between these two. And if we use our minimal basis set, E3 lib, we see actually quite a small error in the basis set incompleteness energy, and that's just a consequence of error cancellation, which is great. With the ACPs, the error goes up a little bit, but not so much. When we go to a double zeta basis set, we see rather large errors associated with this folding energy, 60 and 80 kcal per mole with these two basis sets. With the ACPs, those errors drop by an order of magnitude. And what's really nice to see here is relative consistency across the different ACPs for these 3 basis sets. So we had error cancellation in this case. We had less error cancellation in these 2 cases, but with the ACPs, we see consistency. So that bodes well for applying ACPs to protein structures. So, with respect to the thermochemistry, both the thermochemistry and the non-covalent interactions, the ACPs that we developed using B3 lib seem to be completely transferable across common families of density functional methods as well. So even though they were optimized for D3-lip, the errors associated, the errors that we get out when we apply them to D-lip or LC, maybe PE, or whatever your favorite density functional is, unfortunately, you want them in super functionals because they're kind of strange.
In that sense, are you using the same ACP?
Same ACP that was developed with D3-lip,
Okay.
used just directly with other functions. So you see consistent behavior in terms of the reduction in errors with respect to thermochemistry and non-organic interactions as well. And a few other examples of this particular ACP is developed for use with country clock minimal basis set. Again, the idea behind this is that can we develop a really fast error-corrected method for calculating structures of large molecules like programming protein or something. And so this is the work of Vicky, who showed that with some of these supermolecular binding complexes, you can calculate binding energies if they're non-covalent binding energies to within a pretty good accord with the high-level reference calculations and only seconds or minutes in terms of computations. So quite nice performance. And here's another example. In this case, Vicky performed full geometry optimizations on these supermolecular binding complexes. Again, a couple of hundred atoms in these ones. The kind of light blue shading that you see is the optimized structure overlaid over the reference structure. So these supermolecular complexes look the same after we optimize them with minimal basis set R3 plot with the ACPs. And so this is very nice, and also the binding energies again turn out to be quite good. Yet another example, ACPs that the ACPs developed for D3-lip, I showed you earlier, just applied using CAN D3-lip in this, just for this is a project that we had, looking at binding in these magnesium complexes, studying the hydrogen ion transfer between this benzyl alcohol and keto radical using solvent, optimization frequencies, and so on. And you can see the difference in calculation times, even going from minimal basis set to a double zeta basis set. For the optimization time using double zeta basis set, it was 4 hours. For the minimal basis set ACP, it was 27 minutes. That's a tenfold increase, so 8 to 10. But for the frequencies, we see a 70-fold decrease in the amount of time at a time with good accord. This optimized structures shown here, they're not really differentiated. So excellent finding. Thank you. All right, switching gears. I should have mentioned earlier that when I change the color at the top, it means I'm talking about a slightly different topic. So in this case, we decided to have a look at water. For some reason, people think water is very important, and you can spend a lot of time after that. What it is. And so we decided to look at this as well. It turns out that water clusters are extremely difficult to treat using density functional theory. And in fact, there is no good density functional theory for treating water clusters. You just don't get the right energy ordering in water clusters of particular size. You don't get the right binding energies at all. So we said, okay, let's develop an ECP for water clusters. So system specific. Yes, I get it. Okay. So in this case, we chose pH and H lip as a functional that we're going to correct, and we're using a fairly large basis set for the water. pH and H is one of the least bad density functionals for water. It's still not great. And we developed ACPs to fix the H and H for water clusters. So here I'm showing you on this plot mean absolute errors in water and the binding energy, calculated binding energy to water clusters ranging in size from 2 to 10. Each one of these has multiple confirmations in there. So the whole data set, I can't remember, is maybe 40 or so water clusters. So if we use pH and H, this basis set, with no dispersion correction, we get the red curve. Oh, well, it must, getting large errors must be because we're missing dispersion. No, if you include Grimmett D3 dispersion, you have the same errors. And if you include Becky and Johnson's XDM dispersion correction, you get exactly the same thing. So really terrible, and nobody can rely on these results for anything. The ACP results are sort of on this plot as well. They can't be seen because they all run along the x-axis. So there's an inset here, or I think a separate plot. There it is there. These are the ACP results applied to each of these three methods. With the mean absolute errors shown here. So the largest mean absolute error that we see is 0.2 kcal per mole, 0.2 kcal per mole. Well, I only have
5 minutes.
left. Oh, I should have asked how much. Okay, let's skip this one then. So this is tiny. This is 0.02 kcals per mole for water molecule. So we can now treat or use this method to explore water cluster structures of almost arbitrary size. And we have done that. The next slide shows it, but since I only have 5 minutes, we'll skip over it. Go to the next one and one after that. Okay. Again, the system-specific ACPs. In this case, we're interested in looking for potential energy surfaces with wave number level accuracy, so we can get spectroscopic quality predictions of these calculations, and people can use the potential energy surfaces we generate for quantum dynamics equations. So this is our first go at this, and this is my PhD student Massa who worked on this and recently published it. For the HFCO molecule, small molecule, we were interested in the entire potential energy surface. The molecules and dissociation fragments are shown here. And we developed ACP specifically for HFCO. Next slide shows how we do for vibration frequencies. These are enharmonic vibration frequencies. And we can get down to mean absolute error, 3 wave numbers in accuracy. Actually, V3 limp isn't so bad, but some of the errors even are quite large. Next slide, please. This shows the relative energies of all of those stationary points on that potential energy curve that I showed. Errors in wave numbers, V3 limp, with up to 2,000 wave numbers error. ACP is the largest error we see. There's tiny energy. So we're now looking at uracil and some other molecules of which are still of interest for this. Slide, please. Okay, so this is the getting close to the end. I'm going to skip over the rationale, but actually I can't. There's this. We read this paper a couple of years ago in Nature Communications. That it's a very nice work, and it's a very interesting paper to read. I highly recommend it. In this paper, they say that they develop a machine learning model that can predict bond dissociation enthalpies within chemical accuracy. Computational chemistry speak that means a kcal per mole, depending on what you're working on. And they had to use 290,000 bond energies to train the model. So we're kind of scratching our head around this. It didn't seem right to us. Next slide, please. This is actually what bond dissociation enthalpies look like for a set of 4,400 bond energies. And this doesn't really look like chemical accuracy to me. So the folks who published this paper that I showed you used MO6-2X with a triple zeta basis set, normally a very good method and trustworthy, to train their machine learning model. The machine learning model predicted bond energies within 0.6 kcal of MO6, but this is what MO6 looks like. So, so this is a problem. If folks are generating machine learning models and telling you that they're getting chemical accuracy, they're using density functional theory data to train those models. And density functional theory is insufficient because of this. So we tackled this as well. We developed ACP specifically for bond energies, and the next slide shows the method that we use. This is the base method. It shows a double zeta basis set. it's an unconventional one, chose it for a straight reasons. But anyway, along with this functional, and the data are, of course, are even worse than almost 2x with triple zeta. The blue bars here show the spread of data. We developed our ACPs and applied it to this problem, and the next slide shows what happens with the data. The bulk of the data gets smushed up in between plus and minus 1 kcal per mole, which is the kind of chemical accuracy that when we say chemical accuracy, that's what we're talking about. So very nice. This is published recently in Machine Learning Science and Technology. We did the same thing with barrier heights with action energies. Just quickly show you those. Again, same kind of thing. And with barrier heights, the difficulties are even greater because for every 1.4 kcal per mole error barrier height, that translates into 1 order of magnitude error in rate constant. So if your barriers are off by a lot, your rate constants are going to be off by orders of magnitude. So same thing here. We able to calculate most of the data with this plus or minus 1.4 kcal. Next slide, please. Okay, so this summarizes it. I'm going to skip it and go to future work if I have time. This is fixing wave function theory. And so up to now, I've been talking about using ACPs and a database of chemical properties to fix them. In this case, we're going straight for the total electronic energy. We never thought we would be able to do it, but Omit's work here is showing us that we can. So what I'm showing you here, each dot represents a molecule, and the x-axis is the Hartree-Fock complete basis set total electronic energy for that particular molecule. Omid developed ACPs for use with Hartree-Fock with a double zeta basis set to try to bridge this gap. And the green dots are the corresponding total energies for these molecules. So he is able to, if the next slide shows a close-up of this region, some examples of molecules. So we go from a mean absolute error of over 100 kcal per mole down to sub kcal per mole in total electronic energy with a maximum error here. Actually, there are 14 outliers here. We think that we'll need to run calculations or we have unstable functions or something. But the bulk of the data sit in straight line. So we're working on improving that. The next stage is to do the same thing with correlated electronic energies. This is a much smaller data set, but Omid is showing quite some performance. And with that, I'm sorry to rush through the last little bits of this, but I thank you again for your attention. Folks online as well, and all the help getting set up. This picture is a picture of the place in the world that I live. It's wine country in British Columbia, and it almost always looks like that.
Thank you.
Questions, comments, Professor Oedireta?
Hi, this is very nice talk. I have two questions. The first is related to the trading set. So there are, so you put, for example, for non-covalent interactions, you put dimers, trimers, carbureted with a very large basis set.
Yeah, typically we would use, for those we would use couple cluster single doubles with perturbative triples and extrapolate to a complete basis set limit, but usually something like triples they get and say extrapolation.
Okay, and then if you want to reproduce a complete potential energy surface, you do also the coupled clusters of the whole potential.
Yeah, that's exactly it. So for potential energy surface, if you want to do dynamics on a PES, you need, for that small molecule, our colleagues were using 2,500 data points, each one calculated CCSDT complete basis set. We developed our ACPs using E through LIP with a triple zeta basis set. So we're able to calculate the entire potential energy surface with the ACPs at, I think, 1/10,000th with the same three-way number.
Okay, and second question is when you present the results of the comparison of these big structures that were proteins and the other, I don't remember what kind of systems were it. And you mentioned that you reduce the error. What is the reference energies there?
In the case of the protein, it was, that was for a complete basis set. Or an incomplete basis set is a basis set incompleteness is the energy error. So the reference was a complete basis set. In the case of the protein, the best we could do was triple zeta basis set. So this is too large to go further. This is a problem that it's not quite clear how we're going to tackle. Once we get to very, very large systems, what becomes the reference? Because we can't calculate a couple cluster protein. And so it does become a challenge. Thanks.
So much here.
Related to using these basic keys for calculations of real systems, maybe Christopher, have you find some specific challenges of designing ACPs?
The biggest challenge is in the development. And when we were focused on ACPs to improve properties, the problem becomes the absence of reference data. So transitional chemistry is a great example. So there isn't not very much good data in the literature on transitional, like ligand binding agents, for example. And in part it's because there are problems. A lot of the interesting cases are multi-reference cases. So it's difficult to understand. That's a big one, the reference data. We originally thought that we needed a lot of reference data, but we've since learned that we only need a couple of hundred, maybe 1,000 reference data, so that's positive. But to mitigate that issue, if we're able to correct total electronic energies, then the reference data problem disappears because we can just calculate the total energy. We don't need to worry about multi-reference character and so on. We find a way to get some total energy. We can correct the total energy. Then all the properties will follow. Just calculate the properties. Does that make sense?
Yeah, thank you.
Another one? No, I have a comment. Okay, and one question. Well, when you use the virtual lead, for example, your results are not coming from only virtual lead. Speaking strictly, you have virtual lead plus an additional term, which is taking into account several phases from virtual lead. And you are writing that term in terms of the effective computations. Is it?
I'm not sure what you mean. V3 lab is itself a combination of
Plus an additional term for the total energy.
yeah.
For that reason, you are improving the results from V3.
Yeah. So it doesn't matter. So our target is a particular energy or property. And whatever the underlying methodology gives us as the base energy, the ACP will work on that and get us to the reference.
Here is my question.
Yes.
You can use some empirical methods.
Yes.
For that reason, you will have a faster method because you can include the
Yeah, that will require programming.
Okay.
So yes, yeah. But cracking open a semi-empirical approach like PM7, it works. It works okay. Can be improved. Maybe they can be improved.
We've talked about it, but we still
A lot to cover without breaking open codes.
Yes. Now, another question. If we want to use your these piece, are they published in basic art or something like that?
Well, I was going to make a joke and say you have to give me money, but no, they're all open. They're all open and ready to use. And
Yes, because we are not using, we do not use the browser. So we use software.
Yeah.
But we need just the
yeah. But here's the thing with Gaussian. Oh no, they're not built into Gaussian or anything like that. So each paper that we publish comes with the DCPs associated with that particular method, and also an example input file on how to use it. And for anyone who wants to use them and can doesn't want to wade through all that, they can contact me directly and I'm ready to share. But here's an important thing. So Gaussian has one of the most efficient monoelectron evaluation packages of all computational chemistry programs, including the ECP module. So the calculations, when we use ACPs, the calculation time is almost the same as the applying method, usually plus or minus 5% or so. But if you were to use something like OnePath, the calculation time could increase to 30% because the one electron, at least the effective core potential module is not.
We use NWChem and TerraChem.
I don't know how efficient. It should work well with TerraChem.
Yeah. We're thinking.
Okay. Yeah. But we don't have ACPs for transition metals yet. Are you using TerraChem or?
No. We are not using precision.
Okay. Yeah, I think TerraChem should be.
Okay. Another one?
Yeah,
The last one. Okay.
the very last one. Is I wonder if
Japan.
one can get a meaning to this potential. Now you are using that for correcting the basis sets. But for example, if you try to push your Hartenfock calculation to reproduce copper crystals, that possible and this potential we have to and do one step to correct the complete basis set and then the next one to correct the whole correlation.
Yeah.
That should be possible.
Well, that's what we're working on now. It was up for a very short period of time. I apologize. The very last plot that I showed you was for predicting MP2 energy, MP2 complete basis set energy on the basis of a Hartree plot on the Ciclo function. And the errors were around the mean absolute error was about a K in total energy. It was a smaller data set. We're still working on it, but that's our goal. We can predict accurate, correlated, complete basis set, total electronic energies on the basis of a Hartree.
Okay, thank you very much for your presentation. And your certificate is now in the screen. El Departamento de Química de la UAM Iztapalapa otorga la presente constancia a Dr. Gino DiLabio por impartir dentro del ciclo de seminarios del Departamento de Química del trimestre 24I la conferencia Informing the Accuracy of Quantum Chemistry Methods with Optimist Effective Potentials. El día de hoy, 19 de abril de 2024, firma el Dr. Jorge Garza Holguín, jefe del Departamento de Química, y el Dr. Edgar Carrera Crespo, coordinador de seminarios. Muchas gracias por la presentación. Thank you very much for the presentation. Agradecemos también la presencia en el Salón de Seminarios R206, a todos los que nos acompañaron, y también a los que nos siguieron por el enlace en YouTube. Buenas tardes, somos Departamento de Química, somos UAM Iztapalapa, somos Panteras Negras.
Thank you so much. Thank you very much.